Hello, welcome to the next lesson. I'm not sure what number we're on of the network science class as part of the Bioinformatics Virtual Coordination Network. My name is Jacob Cram from Hornpoint Laboratory. I'm going to share my screen and start the slideshow. So today we're going to be talking about time-lagged time series networks. So in time series, you have a bunch of data, and the data are in a series. So you can imagine you could have a bunch of different columns representing different variables. In this case, each column, and this figure here of each column represents a different operational taxonomic unit, or OTU, and each row is going to represent a different time step in that time series. And each row follows from whatever happened in the row one higher than it. And usually these data are going to be from the same sample, same location. Sometimes you can have replicates. There's additional ways to get into that. But what we're going to talk about today is one way of approaching time series data and looking at how things associate with each other, especially how different variables might lead or lag changes in other variables. So one way that we can do that, so you can imagine that we have 4 variables, A, B, C, and D, and they're all related to each other with time lag. So you can imagine that A changes in abundance. When A goes up, B goes up too, and when A goes down, B goes down too. And we say those are positively associated variables. And we could, if we're drawing a graph, we could say A and C are positively associated. We draw a solid line between those. And A and D are negatively associated, right? When A goes up, D goes down. When A goes down, D goes up. So we say those are negatively associated. We could draw, say, a dashed line between them. And the third kind of association is when A goes up, B goes up. Where's B? B is here. A goes up, B goes up 1 month later. When A goes down, B goes down 1 month later. We say those are associated with a time lag. So we draw a line, an arrow, from the first thing that changes to the second thing that changes. And when we have lots and lots of variables, we can start to draw networks with arrows delineating which direction changes happen in, and those time lagged associations can be informative, and maybe suggest two things that might be happening in whatever location you're running that time series in. So what we're going to do is run through steps that I take when I'm building a time series network. Important caveat here is that I'm not a statistician. I'm a microbial ecologist. And I understand that there are lots of good models out there for dealing with some of the statistical characteristics, I should say, some issues in time series. I haven't seen these applied. So for instance, one would be the autoregressive moving average model. Also, general additive models can sometimes take into account some of the time series structure of data. I haven't seen these applied to network analysis so far, and so in this tutorial we're not going to get into them. But just understand that there are some issues with the time series data. Statistically, don't behave entirely like data that are, say, randomly that are not in a time series, and that you may need to think of that, especially when your paper is coming back or going out to review. And we'll talk about some of those issues at the end of this lecture. So one of the first things that you need to do for most of the statistical approaches that we're taking is you need to deal with missing time points. So, and this is true. So sometimes you'll have lots of variables, have a couple of NA scattered through them, but you can imagine with a time series, if you miss a month, or if you've got a monthly time series and you miss a month, and if you're doing oceanographic work, that's very likely if you've got, say, some months where your boat breaks or you have bad weather, you may need to deal with those missing months. And you can't just, one thing that some people do is just omit them, but then keep in mind that your analysis often assumes that everything happens the same distance apart from the other thing. So what you can do is what some people do is interpolate the missing data. So you can imagine we've got 1, 2, 3, 4 points, and then we're missing a month here. So this value here could be anywhere, but what we could do is we could just draw a line between everything and say, okay, we're going to stick this point wherever that line fits. Or instead of doing a line, we could do some other sort of curve. We could do a spline. Keep in mind that when you do this, you've now added 1 extra point to the number of total points you have, even if you don't actually have any additional data. So that can screw up your statistics. And if you're feeling ambitious, you can statistically correct for having added extra points. We're not going to do that here, though. I'm just going to acknowledge that we've added an extra point. if we say were to write this up. So again, here we've got our example table, time points on the columns, OTUs on the rows, and we're interested in time-lagged associations between them. So one thing that we can do is we can just copy this whole table over and shift it by 1 month. So now we have all of our OTUs, and then we have another set of columns with all of our OTUs lagged by 1 month. So just one month lower. And then of course we've got this one here and this one here that don't match with stuff over there. And so we end up cutting into sort of our number of samples. We'll just delete the one off the top and the one off the bottom. So now we've got our big wide lagged correlation matrix. And then what we can do is we can basically just do whatever statistic we were. So remember in previous lessons, we've basically done all the OTUs versus all the different samples, and we do some sort of network, or we build some sort of network. We do a correlation network or a sparsely seeded network on this. Similarly, you can do the same network on this whole data set. So you'll have you can do the Spearman or sparsely seeded or some linear model, but you want to do that to every pair of variables. So you're going to come out, and I didn't show this. You're going to come up with a matrix where every row, you're going to have the same number of rows and columns, and each row and column is going to be each one of the OTUs, and then you've got them lagged and unlagged. So then what you're going to have to do once you have that thing is you're going to reshape it into a way that's meaningful and that you can plot in a graph. So some post-processing is going to be in order. So you can imagine after a little bit of reshaping, we're going to have data like this. So here we're just looking at 2 operational taxonomic units, whereas in real life we'd probably look at more operational taxonomic units versus 2, 1 versus 3, and so forth. But for each pair of units, you're basically going to have 4 different associations, right? We're going to have 1 versus 2. We're going to have 1 lagged versus 2 unlagged, 1 unlagged versus 2 lagged, and both of them lagged versus each other. And then you're going to have some score for each one of those, and you're going to have some sort of p-value for each one of those. Now keep in mind that in this particular case, we've got OTU1 versus OTU2 has some score. OTU2 lagged versus, sorry, this is meant to be OTU1 lagged versus OTU2 lagged, would have the same score, right? So we have two variables and we just both shift them both down 1. We haven't really done anything to them, so we're going to get the same score out of that. It's essentially this row and this row are going to be redundant with each other, whereas these ones are not. So, and then in this particular case, we have sort of a better score. We lag this one than we do when we don't like either of them. We have a worse score when we lag OTU2 than when we don't like either of them. So again, in real life, you have more than just 2 OTUs. Also, I'm doing this in Excel just to show you, but you probably shouldn't actually literally lag your data in Excel, but you could. So then we have that redundant row with lag versus lag, so we'll just pull that out. So now we have only non-redundant information. And so once we have our non-redundant information, at that point, we can do a false discovery rate correction. So any number, we've gotten into sort of some examples of false discovery rate corrections that you can do, but you'll do that now. And then once you've done your false discovery rate correction, well, before we go too far, so once you've done that, then you probably want to recode all your stuff. So then instead of saying having each pair of things, we have them coded as a delay. So here we've got, this is the data we had before. And we'll say, we'll just make 2 new variables, which are without the word lag in it, and we'll make a third one, which is which direction the lag goes. So we've got 1 versus 2 is a delay of 0. 1 lagged versus 2 would be a delay of -1, and 1 unlagged versus 2 lagged would be a delay of 1, even though I wrote 0 there. Which is one of the dangers of doing everything in Excel. Here I've cleaned it up. So you'd end up removing the columns you don't want. So we've got OTU1 versus OTU2 with our different delays and all of our stuff. And then once we have all of this, and since we've already done our false discovery rate correction, accounting for the fact that we've got additional comparisons beyond what we've done if we didn't do the time lag, then we can say, well, which one of these is the strongest association? In this case, this one is the highest score. So we'll say, we'll take OTU1 versus OTU2. And then we just have 1 line out of those 3 different ones. But since we're doing this for every pair of variables, we'd be doing this over many more things. We basically would reduce the number of things that we have to about 1/3 if we're doing a delay of 1. You could also do the same kind of analysis with a delay of 2. So then there you'd shift it by 1 and you'd shift it by 2 and you do the exact same analysis. And once we have this, then we can draw some sort of graph. So here we say, okay, OTU1 happens first, and then it leads a change in OTU1 by whatever unit of time we're looking at, say 1 month. So just a couple issues that I want to get into with this approach that, I mean, I've used this approach in my analysis before, but I recognize that there's some issues about it. One of them is seasonality. So if you just have a bunch of OTUs and you haven't put seasonal information in there, it's likely still driving a lot of your effects. You'll likely see a lot of clustering related to season. So one thing you should consider doing is doing some sort of analysis that allows, I mean, especially if your analysis allows you to put environmental data in, or you're using like a Spearman network, this doesn't work so well with sparse CC, you could include one or more season variables. So in my analysis, I'll often, for seasonality, put in as variables the day length and the rate of change of day length, and those together kind of tell me whether things are, if the rate of change in day length is the thing that everything's related to. They're happening in the spring. If day length they're related to, then they're happening to summer, and so forth. One thing you can also do if you want to, if you say want to look at relationships between OTUs that aren't all driven by season, is that you could correlate everything to season, or do some sort of linear model relating everything to season, and subtract out the seasonal term and essentially just look at the residuals. And that might be informative for some sorts of analyses. The other issue that frankly bugs me a little bit about this approach is autocorrelation. And that's essentially that values that are close together in time are going to be more similar to each other in any sort, in most time series, than values that are further apart in time. And what that ends up meaning is that if you've got, imagine you just had variables that are drifting around randomly, with no actual informative link between the two of them. But if they change slowly enough, you're essentially going to start to, just due to that pattern, you're essentially going to have things look like they're associated with each other. So the autocorrelation will end up inflating your scores some. And so you should certainly address it in your discussion section, but also consider using statistics that adjust for this. So for instance, you do an autoregressive moving average or some sort of GAM. If you find good ways of doing this in a network analysis, let me know. I'm really quite interested in it. I just haven't gotten it working. So you can do all of this analysis by hand in R. And so I'm going to risk jumping out of this tutorial here. I'll show you some R code. So here we have, this is pushed to the GitHub repository with all of the other analysis that we've been doing. Essentially here what I do is I load in some example data. This is from the San Pedro Ocean time series. And we just do a number of processing steps, right? So we set up the data. I just pull out the most abundant data. We do some pre-processing. We do a standard log ratio transform. We do Spearman correlation, and then we essentially wrangle the data to deal with the time lags, just like we were talking about. And then we'll plot it up, and we get a plot. So then here's our plot, and we still have our different OTUs, and then if they're connected to each other, you draw an arrow from the one that happens first to the one that happens second. And also, so this was for a Spearman network. I also do this for a sparse CC network. The analysis involves a few extra steps, just as in general, sparse CC networks involve a few extra steps, and then basically you get another network that looks relatively similar to the Spearman network in this particular case. So in addition to doing things in R, you can do them in another program that Charlie Shaw, formerly at USC, wrote, and that I'm a co-author on. I helped with some of the analysis, called Extended Local Similarity Analysis. So a slideshow from current slide. So we'll just jump to the end of this. So extended local similarity analysis can do a lot of the stuff that we can do ourselves in R, but it also implements some additional approaches, which I think are pretty nice. So you can do a Spearman network in ELSA, but you can't do a sparse CC network in ELSA, just because that wasn't a thing that got coded into it. It's a little bit trickier to run. Setup installation isn't too tricky with it, but just getting all the data into exactly the right format is a little bit finicky. We'll talk about how to run ELSA in upcoming weeks. It has some real advantages. It can look at you can have replicates in your time series, and it can sort of statistically think about replicates. It's when everything's been pre-coded for you, and it has some ways of pre-normalizing the data. And also we've built in some new stuff to look at trios of nodes instead of just pair of nodes. But ELSA is beyond the scope of this lecture for the most part. that should be that. If you have any questions, come by our office hours, or if you're coming to this well after the fact, send me an email.